Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Sridevi classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist we will understand one very popular and important board examination question, suspended coil galvanometer, and we will understand its construction and working in good detail. We'll also learn how calculation of shunt resistance and multiplier resistance is done respectively to convert galvanometer into an ammeter or a voltmeter. We'll also solve some exam centric numerical problems. So let's start suspended coil galvanometer, a very favorite board examination question. Suspended or moving coil galvanometer has a current carrying coil which moves in the magnetic field of permanent magnet. These permanent magnet moving coil instruments are most sensitive and very accurate measuring instrument for measurement of current and voltage in DC circuits. In fact, the working magnetic field of such instrument is the strongest, and such instruments generate highest torque to weight ratio to produce most sensitive and accurate measurements. The magnetic part of these moving coil galvanometer consists of a pair of north and south magnetic pole made of a very good hard magnetic material such as alnico steel, along with a soft iron cylindrical core in between these poles. Now the combination of horseshoe shaped permanent magnet and soft iron core produce a strong uniform radial and horizontal magnetic field. Around this moving coil turns a light non-magnetic and good conductor metallic rectangle frame is vertically mounted on a shaft and pivoted in hard Zevel bearings. Now this metallic frame is free to rotate between pole and core in the working magnetic field. Fine insulated copper wire turns are wound on this metallic frame to form a rectangle coil, and the two ends of moving coil are connected to two spiral springs made of phosphor bronze. These elastic and electric conductor springs acts like a flexible current carrying contact for this moving coil. Now when this galvanometer is connected to electric circuit, current passes through coil turns and current carrying coil conductor experience force in working magnetic field of permanent magnet. The magnetic force on turns of this moving coil of two vertical sides form a force couple that produce a rotating torque and generate a deflecting torque in this moving coil mechanism proportional to the current passing through the turns of coil. By the deflection, the elastic phosphor bronze material of spiral spring get distorted, and elastic member of phosphor bronze spring produce a restoring torque equal and opposite to deflecting torque. During motion, this rectangle metallic frame of moving coil cut magnetic force lines of permanent magnet, and change of flux linkages induce EMF and eddy current in it, and those eddy current act against frame movement and produce a damping action against movement of moving frame and coil, and due to that damping, the equilibrium of deflecting torque produced by magnetic force on current carrying coil placed in magnetic field and controlling torque produced by distortion of spiral spring generate an equilibrium position of moving mechanism without oscillation, and that final equilibrium position of moving system is measured by a light aluminum pointer which is attached to moving mechanism, and equilibrium position of pointer on calibrated scale gives us the reading of current passing through this measuring instrument coil. Working principle of moving coil galvanometer is very simple. The current carrying conductor sides of coil turns are placed in working magnetic field of permanent magnet, and they experience magnetic force by the interaction of current and magnetic field. Since the magnetic field produced by horseshoe shaped permanent magnet and soft iron core is radial, so in all position of this moving coil, the coil plane always remain along the field lines as shown in this diagram, and in that condition two horizontal sides BC and DA here got angle between current and magnetic field either 0 or 180, and when current and magnetic field both are in the same line, there won't be any magnetic force. But these two vertical sides AB and CD have 90-degree angle between current and magnetic field, and in that case n turns of coil each carrying I current for this L vertical length in this B Tesla magnetic field of permanent magnet experience NBIL force. As for 90-degree angle between magnetic field and current, sin nt will become 1. So in this force relation, N is number of turns in coil, B is working magnetic field flux density in Tesla, I is current in coil turns, and L is this vertical length of coil turns, and the direction of force on current carrying vertical side AB and CD is obtained by Fleming's left hand rule. And for that, the thumb, forefinger and middle finger of left hand are stretched mutually perpendicular, and the fourth finger is directed along the direction of magnetic field from north pole to south pole, here horizontal, left to right. And through wrist or elbow, left hand is twisted such that middle finger get aligned with vertical downward AB current. Then the thumb of left hand indicate towards us the direction of force as denoted by dot here, and when hand is twisted such that fourth finger remain in the direction of magnetic field and middle finger comes in vertical upward CD current direction, then the inward direction of thumb indicate the inward denoted by cross direction of force on CD vertical side. Now these direction of force can also be analyzed from this diagram observed from top. This AB current is inward current and this CD current is outward current, and magnetic field is N2S as shown here. So according to Fleming left hand rule, the thumb indicate the direction of force on AB side, and again thumb indicate the direction of force on CD side. Two vertical sides of this rectangle coil AB and CD have forces of equal amount NBIL, and the direction are opposite to each other, and two forces won't act on the same line. So these two forces form a force couple, and that couple try to rotate this moving mechanism, and the rotating torque developed by the force couple is equal to force multiplied by normal perpendicular distance. And for radial magnetic field, the force is always tangential, and the normal perpendicular distance between two force lines is always the width of coil. And if the width of coil is B and force is NBIL, then torque is force multiplied by normal perpendicular distance, and length and breadth, length in fourth relation and breadth in torque relation, become area of this rectangle coil. So the torque produced in this current carrying coil placed in magnetic field is equal to NBIA, where N is number of turns, B is magnetic field flux density of permanent magnet and soft iron core, and I is current in coil turns, and A is rectangle area of this coil. Now this deflecting torque produce deflection in moving mechanism, and that deflection distort the two spiral springs used to allow current in moving coil, and the elastic member of spiral spring produce a restoring torque against deflecting torque that act as a controlling torque, and the amount of controlling torque produced by spiral spring when spring is quite long and thin is directly proportional to the amount of angular deflection of moving mechanism. And if amount of angular deflection is theta and stiffness coefficient of spring is C, then the control torque produced by spring become equal to C theta. Current in N turns of moving coil in magnetic field of B Tesla of permanent magnet produce magnetic forces to develop a rotating deflecting torque. And if A is cross section area of rectangle coil turns, then Bina is deflecting torque, and due to that deflecting torque, moving system start angular acceleration and deflection, and due to that elastic spiral springs of moving mechanism get distorted, and they generate a restoring opposing control torque proportional to amount of deflection, and proportionality constant is known as stiffness of spring. If spring is thin and flexible, the value of C is small, and required control torque is produced by sufficient amount of deflection. And during motion, when this metallic frame of moving coil moves in magnetic field, flux linking to metallic frame changes with respect to time, and that induce EMF and current in metallic frame, and as per Lenz's law, induced eddy current act to oppose the cause, that is motion of moving mechanism. So due to eddy current, damping will take place and moving mechanism will get final equilibrium stable position without much oscillation or delay. And when equilibrium stable position of moving mechanism is achieved, oscillation has ceased, the damping will also eliminate, and only deflecting and control torque will produce an equilibrium. As two torque are opposite and with certain amount of deflection, control torque become equal to deflecting torque corresponding to current, and this equilibrium condition can measure current in terms of amount of deflection of moving mechanism that can be obtained on a scale by position of pointer. Now this ratio of stiffness coefficient to product of magnetic flux density, number of turns and area is given another name, galvanometer constant G, and we can say on a linear scale proportional to amount of deflection, current can be measured by appropriate calibration directly in amperes. How sensitive a galvanometer can measure current or voltage is known as figure of merit. Figure of merit is defined in terms of current sensitivity for an ammeter and voltage sensitivity for a voltmeter. Current sensitivity is defined as deflection per unit of applied current. We know in a moving coil galvanometer at equilibrium, deflecting torque beta become equal to C theta, and from that equilibrium rearrangement can give us ratio of deflection to measured current or deflection per unit of applied current, and that is called current sensitivity, and current sensitivity will become ratio of product of magnetic flux density, number of turns, area to stiffness coefficient of spring, and this expression clearly indicate that sensitivity can be increased by having higher amount of deflection for smaller amount of current, and that can be increased by increasing the strength of magnetic field flux density. The permanent magnet with soft iron core produce a very strong working magnetic field to have higher amount of current sensitivity. Sensitivity can also be increased by increasing number of turns in moving coil, but when we increase number of turns, it increase the weight of moving system. Increased weight may increase friction in movement, and that can reduce accuracy. So there are certainly some limit in increasing number of turns. Similarly, if we increase cross section area of moving coil, it will increase deflecting torque and sensitivity to have higher amount of deflection for smaller amount of current. But when we increase cross section area of moving coil, it not only increase the size of meter but also increase inertia of moving mechanism, and that will reduce the dynamic response of moving mechanism. Now one good way to increase current sensitivity is to reduce stiffness coefficient of spring, or to use a spring of greater flexibility and smaller thickness. So a flexible thin spring can have smaller value of stiffness coefficient, and that results in increased amount of deflection for same amount of current or increased current sensitivity. For a voltmeter, the figure of merit is known as voltage sensitivity or deflection per unit of applied voltage. We know when we apply measured voltage across galvanometer, and if voltmeter circuit coil and multiplier got a total resistance RV, then current in circuit is given as V is equal to IR, and in place of deflection per unit current we can write B N A over C, and deflection per unit voltage will got this relation. So voltage sensitivity is also directly proportional to working magnetic field flux density, number of turns or area of moving coil, and inverse of stiffness coefficient, but it also depends upon resistance of voltmeter circuit, and it is inverse function of resistance. So a voltmeter of lower resistance will have higher sensitivity or deflection per unit of voltage. Now range and sensitivity become contradictory to each other. To have a higher range measurement, we need a voltmeter of higher resistance, and when we increase resistance of voltmeter circuit by higher amount of multiplier, the voltage sensitivity will get compromised. In board examinations, advantages and disadvantages of moving coil galvanometer are often asked. So as far as advantages is concerned, moving coil galvanometer are most sensitive and accurate current and voltage measuring instruments for DC circuits because they have a very strong working magnetic field. At equilibrium, when deflecting torque become equal to control torque, we found that measured current become a direct proportional function of amount of deflection. So that gives a linear measuring scale, and linear measurement scale are not only convenient and easy to measurement, they are also convenient for calibration. So this is a great advantage that moving coil galvanometer got a linear measuring scale. From the same galvanometer, when we connect a small resistance shunt parallel to coil, we can convert galvanometer into an ammeter, and when we place a higher amount of multiplier resistance in series with galvanometer coil, the same galvanometer can measure higher amount of voltage. So both voltage and current measurement can be done by single measuring mechanism. The design of moving coil permanent magnet instrument is such that permanent magnet produce a self-shielding arrangement and external magnetic field can't produce error in such measurement, so they are free from stray magnetic field error. The same moving mechanism can be used to measure both current and voltage, that too in different ranges, by appropriate selection of shunt and multiplier. So it is in true sense multimeter which can measure multifunction, that too in multi-range. But this instrument also got some disadvantage. The most fundamental disadvantage of this instrument is that it cannot measure alternating current. In alternating current, after every half cycle, current reverses its direction. The direction of magnetic force and deflecting torque also get reversed, and full cycle average value of alternating current is 0, and corresponding to that, the average torque produced by moving coil instrument for alternating current will become 0. So alternating current will be read as 0 value by these moving coil instruments. They cannot measure alternating current. These permanent magnet moving coil instrument are little costly, as alnico steel is a costly material. Typical design of horseshoe, delicate current carrying flexible coil design all make that costly and delicate. They can't handle overloads and may get damaged if current exceed their limits. So they are costly and delicate is another disadvantage. The arrangements to measure higher amount of current in galvanometer is known as current range extension. A basic meter is designed with inherent small current capacity because lightweight moving coil have thin cross section area of turns in moving coil. They won't have good current carrying capacity. Similarly, for higher sensitivity, moving coil galvanometer use a thin flexible spring of lower stiffness coefficient or smaller current capacity. So the maximum current to produce full scale deflection on moving mechanism known as full scale deflection current is very small, and if measured current is quite large than full scale deflection current, the remaining current can be passed to a parallel bypass circuit during measurement, and this small resistance connected parallel to meter mechanism to facilitate higher range current measurement is called as shunt. Now if measured current is I and full scale deflection current is IFSD, then the difference of two is current passing through shunt, and if measured current is M times of full scale deflection current, we are extending the range of galvanometer by M fold, then we can say the shunt current is M minus 1 times of full scale deflection current. It means if to increase range of current measurement by 100 fold, then this I current is 100 times of full scale deflection current, and 1 unit full scale deflection current will pass through meter, but the remaining 99, 100 minus 1 part of full current will pass through shunt. So shunt is designed in such a way that when we are measuring a high current, only scheduled full scale deflection current passes through meter coil and the remaining current get bypassed by parallel low resistance shunt. Now in parallel, the voltage across meter coil and across shunt is the same, and voltage is product of current and resistance. So current in meter to produce full scale deflection and resistance of meter coil become the voltage of shunt, that is current in shunt and resistance of shunt, and shunt current is M minus 1 times of full scale deflection current of coil. And this simple formula, shunt resistance is coil resistance divided by m minus 1 to carry m minus 1 times current to measure m times current compared to full scale deflection. So if we want to increase range by 10 folds, 1 unit current will pass through coil, 9 unit current will pass through shunt. So shunt resistance is 1/9 of meter resistance, as m is 10 here and shunt resistance is 1/9 times of meter coil resistance. This numerical example will explain the concept of shunt. It is given that the resistance of galvanometer coil is 99 ohm and its full scale deflection current is only 1 milliampere. A shunt of 1 ohm is connected in parallel with galvanometer. We have to find out the maximum current which we can measure by this combination of meter coil and parallel shunt resistance known as an ammeter. So in parallel combination the voltage is same, so the product of current and resistance in coil and shunt is the same. So current in meter to produce full scale deflection is 1 milliampere, meter coil resistance is 99 ohm. We have to find out shunt current, as shunt resistance is given 1 ohm and it is obtained that shunt current is 99 times of meter current, as its resistance is 99 times less. So shunt current is 99 milliampere and the total measure current is sum of meter current and shunt current, and it is 1 and 99, 100 milliampere or 0.1 ampere. Appropriate series multiplier resistance connection with meter to measure higher amount of voltage is known as voltage range extension. The basic meter got a reasonable resistance of coil and full scale deflection current is very small. So a very small voltage will produce maximum deflection in this meter, and to measure higher voltage with same full scale deflection current, the current is limited by connection of a high series resistance known as multiplier with meter coil to make it a voltmeter of sufficient range. As meter coil and multiplier are in series, so the total resistance of the two is sum of the two, and as per Ohm's law, current in this series circuit is voltage divided by total resistance, or we can say the total series resistance of coil and multiplier is a ratio of measured voltage capital V divided by full scale deflection current. And if full scale deflection current is not known to us and the maximum voltage which meter can measure is given small v, then in place of full scale deflection current in this relation we can write measured direct voltage across coil divided by coil resistance. And to find out multiplier resistance in total resistance relation, full scale deflection current is replaced as direct voltage across meter divided by meter coil resistance, and in this total resistance when coil resistance is subtracted we'll get multiplier resistance, and this ratio of measured voltage to maximum direct voltage across meter is known as voltage amplification factor. And we got a quite easy to remember formula for multiplier resistance, as it is m minus 1 times of meter coil resistance. And if we recall current range extension relation, then in that the parallel shunt resistance got a value by dividing coil resistance by m minus 1 fraction, and here for voltmeter it is multiplication of m minus 1 factor. And one can remember in ammeter shunt got a smaller value, and smaller value is obtained by division of m minus 1, and in voltmeter multiplier got a higher resistance value, and higher value is obtained by multiplying coil resistance by m minus 1 fraction. The practice of this numerical will make our preparation exam centric. We have given a galvanometer coil got a resistance R coil 12 ohm and it show full scale deflection for a current of 3 milliampere. We have to convert this galvanometer system into a voltmeter of range 0 to 18 volt or an ammeter of range 0 to 6 ampere. There are two parts of this question. Let's first discuss voltage range extension. And for voltage range extension, the higher amount of multiplier resistance is connected in series with basic meter to measure higher amount of voltage, and here the maximum 18 volt when applied across this series combination of basic meter and multiplier, then it will allow full scale deflection current through meter and will get full scale deflection. And in full scale deflection will not measure 3 milliampere from scale but will measure 18 volt from scale. So this become a voltmeter of 0 to 18 volt. we know that total series resistance of galvanometer coil and multiplier resistance is ratio of measured voltage to full scale deflection current. Galvanometer resistance is given 12 ohm, multiplier resistance we have to calculate. The range of voltage is 18 volt and full scale deflection current is 3 milliampere. 18 divided by 3 becomes 6. 10 raised to power minus 3 on numerator side become 1000. So this ratio is 6000, and when 12 is subtracted from 6000, we'll get multiplier resistance as 5988 ohm. So when we connect 5988 ohm in series with this coil, it become a voltmeter of 18 volt range. Now we have to convert the same 12 ohm galvanometer coil having full scale deflection current 3 milliampere into an ammeter of range 0 to 6 ampere. So the total measured current is now 6 ampere, and galvanometer can have only 3 milliampere current passing through it for full scale deflection. So remaining current should be bypassed through shunt resistance. So shunt current is a difference of measured current and galvanometer current, and when 6 ampere is subtracted by 3 milliampere, we'll get 3 milliampere in ampere, 0.003 ampere, and the subtracted result of shunt current is 5.997 ampere. And in parallel connection, voltage of shunt and voltage of coil is same, and voltage is I into R. Meter got full scale deflection current 3 milliampere, meter coil resistance is 12 ohm, shunt got 5.997 ampere current, and we have to find out shunt resistance, and shunt resistance 12 3 is the 36 milli divided by 5.997, roughly it is 6 milliohm. So when a small resistance is connected parallel to coil, it become a ammeter of higher range. In last 22 odd minutes, we have explained each and every aspect of suspended coil galvanometer. You have now understood what is construction of moving coil galvanometer, how it works, how we design shunt and multiplier to extend current and voltage measuring range, and you can also solve the numericals which usually ask in our examination. Our other learning video of this playlist are equally useful, and if you need our online doubt clearing classes or exams and trick notes, do join our membership by clicking join button just beneath. Have nice time, happy learning. Thank you very much.